Since concluding our study of Taylor's series, we've spent a lot of time learning integration techniques, and many of our integration techniques have been quite involved. The truth is, there are some functions that are just blatantly difficult to integrate, including functions we can't integrate, even though we might want to know something about the area underneath the curve. For functions such as this, some of which are displayed on the page, there's really nothing to do other than to approximate the area underneath those curves if we truly need to know a concrete value for an antiderivative. So I've got an example of a function here where I haven't shown a formula for how we've generated this function. So let's imagine that it's a function that doesn't have a basic antiderivative. I'll be working on the interval from 2 to 8, and the function is graphed in blue. And what I've done is I've drawn trapezoids underneath the curve rather than rectangles, because one of the things we saw as a class was that trapezoids seem to more naturally fit the curve of the function than our rectangles do. And trapezoids don't actually have a particularly difficult area formula. For determining the area of a trapezoid, I really like this visual, which shows what the formula is and why it is so. If we begin with a trapezoid, like the one outlined in dark black here, and simply duplicate and rotate the trapezoid to create this gray trapezoid over here, what we end up with is a parallelogram. And a parallelogram and a rectangle have the exact same area formula, the length of the base multiplied by the height. So if the short side of the trapezoid has length A and the long side of the trapezoid has length B, both sides have total length A plus B, and the height has remained constant. So the area of the parallelogram is given by the quantity A plus B multiplied by H, and the area of the trapezoid is exactly half of that. So this formula can be used as an addend when computing Riemann-like sums rather than the formula for the area of a rectangle. So let's take this example and let's see how we could compute this value, this time using something like Excel. Now I'm choosing to demonstrate Excel today because Excel is really good at pattern recognition, and just one or two tricks inside of Excel can make it do a whole bunch of computations for you. So with the function we were looking at, the x values we were considering were moving in unit values from 2 through 8. So if I just start typing in a pattern like 2, 3, 4, it isn't very hard to complete the pattern manually, but I could also highlight those cells in Excel, click on this bottom right corner of the rectangle where the plus sign is, and drag the formula down, and it will complete the pattern for me. Now it turns out for my function that I've shown here, it actually has a specific and easy to program formula. I've just multiplied x minus 1.5, x minus 2.5, x minus 3.5, and so on, all the way till we get to x minus 8.5. I've done that multiplication and then divided everything by 80 to make things smaller. And after all of that is done, I add 9. So that's a pretty easy pattern for Excel to recognize. So those numbers that I multiplied together, 1.5, 2.5, 3.5, and so on. Again, Excel can match this pattern for me and expand it. And now what I can do is I can figure out, well, what is 2 minus 1.5? What is 3 minus 1.5? What is 4 minus 1.5, etc. by simply saying, I want the value of this cell to be equal to this number minus this number, and hit enter. And then Excel will do that computation for me. Now there's one little trick that I'd like to do called adding an anchor to this formula to help Excel get the pattern right, because sometimes when we try to generalize formulas, Excel doesn't exactly know how to generalize it, especially if we only give it a couple examples. So we can help it along with the use of these anchors. In Excel, an anchor is a $sign, and we put that $sign in front of a value that we want to remain constant. So if I want the formula from this cell to generalize when I drag it across the columns, then what I want it to be keeping the same about the C1 formula is the 1 part, but I want to allow it to change the letter to go to D1, E1, F1, etc. So because I want the 1 to stay fixed, I'm going to add that $sign in front of the 1. Similarly, if I were to take this formula and drag it down across the rows, I would want to go from cell B2 to B3 to B4, etc. I would want the value in B to stay the same, but the number to change. So in order to indicate that I want the B to stay the same, I can add that anchor. Now when I hit enter, nothing has changed in this cell. It has still computed 2 minus 1.5, but I can now drag this formula both down and across, and Excel fills in everything appropriately. So these are all the values I'm going to need to compute the output of my function. My function f of x is computed by taking 1 and dividing it by 80, and then multiplying it by all these previous values. So here, this cell times and then when all of that is done, we add 9. If I hit enter, I now get the value of my function at the point when x is equal to 2, and we can see that the output value is matching what we see here in Desmos. Returning to Excel, remember that even though that formula was hard to type, Excel is good at pattern matching, so I can simply drag that formula down, and I've now computed f of x for all of these different x values on my curve. In this example in Desmos, we can see that the distance or the height of each of our trapezoids is just 1. We're working in unit intervals. And then we need to average the lengths of the bases of the trapezoids. So if we wish to compute the area of the trapezoid in between x is 2 and x is equal to 3, we're going to multiply 1 by the sum of these two numbers divided by 2. So let's have Excel do that computation. Let's add this value to this value and divide by 2. Again, Excel can pattern match to do all those computations at once. And we can add up the individual areas of the trapezoids by using the sum formula and highlighting the cells we wish to sum. And we'll get an approximation for an area of 49.60 underneath that curve.